share my screen. All right, so you're able to see my PowerPoint slide now?
Yes, sir.
Okay. All right. Now, just recap what is all those important formula. So the first one is Reynolds number. Reynolds number equal to rho Vd divided by mu, and the magic number 2300. If it's less than 2300, then you're having a laminar flow. And the ratio of L over D, if the number is 0.006 times the Reynolds number, you will get laminar flow. So this formula is suitable for laminar flow. And last lecture, we mentioned that to make the flow flowing in the pipe or in the tube, there are three phenomena. One is the differences of pressure. The second one is we move one plate parallel to each other, or the gravity force. So these are the three reasons making the flow flowing from one direction to another direction. Okay, pressure, moving plates, and also body force, which is due to the gravity. So last lecture, we already seen one example on a piston moving, all right, using hydraulic float SAE 10W oil. All right, today we're going to look at a moving plate scenario. So, for example, we have a bearing and we have a journals that rotate, in this case, in the anti-clockwise. And we have a fluid between the bearing and the journals. So as you can see from the diagram over here, we zoom in this region, you will see that there's a fluid between the journals and the bearing. So in this case, because there's a rotating body, we are having a moving plates that makes the fluid flowing. So today we're going to look at upper plate moving with a constant speed u, and this is an example that we have in the normal life or in engineering application. Yeah. So in this case, we will consider the upper plate is moving to the right with constant u. Which is, in this case, we will use back the diagram. So we have upper plate and bottom plate, and again we have two axes. One is y-x and one is y0 and x0, or y prime, x prime. So we have two different axes over here. So today we're going to look at moving plate at the top. So this top is moving, this is stationary. So what happened to the equation that we'll look at? So since we have a moving plate, we need to look at the boundary condition of the moving plate. So if your y equals 0, there's no movement of the fluid. So your u will equal 0 when the bottom plate doesn't move. So as your fluid flowing, there's a contact between the fluid or on the surface, then the velocity will come to 0 at y equals 0. All right. Now, cool. Are you there? Cool.
Yeah.
So by looking at this screen, so since the upper plate is moving, so what is the next boundary condition that you can write? The first equation for the bottom plate, you write u equals 0 at y equals 0. So the second boundary condition for this upper plate, what is the equation? U will equal to what?
U equal to A over 2.
What is U? What is U? What does U mean?
U is velocity.
So, or 2. So in this case, you're having a moving plate. upper plate is moving with a constant speed, capital U. So what is the second equation for this case? What is the speed of upper plate here? Who?
The speed. Is there 9.881?
On this slide, where can you show me where can you see 9.81?
9.81 is constant, right?
What is 9.81?
Acceleration.
Okay. My question is, what is the speed of upper plate? This upper plate. What is the speed?
0, right?
Oliver, are you there?
Yeah, I'm here.
What is the speed of upper plate? By looking at these slides, what is the speed of upper plate?
Is it X? Wait, Y, T, Y, T, X. In
Let me check. Are you listening to what I say just now? Both of you. Both of you seems not in the class. I repeat one more time. Today we're looking at we are looking at a scenario. What make the flow flow? How can the fluid flow? There are three reasons. One is because of the change of pressure. Second is because of the moving plate. The third one is because of the gravity. We already cover the pressure with non-moving plate. Previous one, both plates are stationary. So meaning if you look at the scenario, this plate and this plate is not moving. Today we'll look at the second scenario where we have a moving plate. Okay, I'll repeat one more time. Today we're going to look at a moving plate. Only one plate is moving, with its upper plate is moving. So we are having a scenario where we have a bearing and the journals or the rod is moving in the center, and the rod is moving in the anticlockwise. And we zoom in this region. So this region is, according to journals, is moving in the anticlockwise direction, so it's moving up, and the bearing is not moving. So the fluid will be moved from the bottom to top. Okay, so this scenario we can simulate as two parallel plates. So in this case, we will consider upper plate here. This is the upper plate with moving with constant speed, capital U. What is the speed, Ku? What is the speed of upper plate?
Constant speed, U.
Okay. Oliver, what is the upper plate speed?
yeah, capital U.
Now you see it. Now you understand my question, right?
Yeah.
Yeah. Okay. So the boundary condition, we have the first boundary condition, the bottom one doesn't move. So your U equals 0. At what location? At Y equals 0, it is here. So what is the second boundary condition? Still back to the question. So what is the equation for boundary condition at this location? What is the boundary condition equation for this location? What can you write? This equation is for this location. So my question is, what is the second boundary condition at here? Oliver, can you try to answer? U equal what? At y equal what?
The y value should be a, right?
Okay, y value a, it is here because it's
Yeah.
referring to the axis. Okay, what is the u value
Is
here?
it still 0?
Y0?
Because it should be still moving at constant speed at the same location.
And your constant speed is 0.
Or u, capital U.
So the second boundary condition equation is what?
Capital U at
U
y equal
equal
to
to capital U at y equal to a, correct?
a. Yeah.
So this is what the answer that I want. Right, cool. Do you see? Do you understand what Oliver trying to say just now?
The upper plate u is equal to constant speed, so the speed is equal to u.
Yeah, correct. So do you understand why the y is a? Do you understand why Oliver say y equal to a? Do you understand?
Because the location.
Okay, so it's count from the bottom, huh? Bottom to top is a, huh? Can you see?
Yes.
Right. Okay, so the second equation is u equal to capital U at y equal to a. So this is our boundary condition. We will repeat the same derivation steps. So after you repeat the derivation step for velocity distribution, you will get u equal to 1 over 2 mu dp over dx y square plus c1 mu y plus c2. To solve c1 and c2, you need to use this boundary condition. First, you apply this one in here, you will get first value of your c1 or c2. Second, you apply u equal u at y equal to a, you will get the value for constant value. So when you apply these two boundary conditions, you'll get C2 equals 0. Your C1 will be equal to capital U mu divided by A minus half dP over dx A. Okay, so this is a mathematics flow. Are you able to explain? If I ask you to explain again, are you able to understand how you get C1 and C2? Cool, are you able to explain how you arrive at C1 and C2? Cool, are you there?
Yeah.
All right. Oliver, are you able to explain? Are you
No,
able to understand?
Could you just repeat one more time?
Okay. You understand how to get boundary condition, right?
Yeah. This one.
Then we repeat the same step to get the velocity profile, this equation. Okay. If not, you refer to the previous slides. I'm not going to repeat how to get this equation. So you refer to the previous slide, you get this one. So inside this equation, you have two unknown there. You have C1 and C2 after you integrate the equation. To get C1, C2 value, we apply the boundary condition. First, you apply the first equation, we did this one. U equals 0, so you write 0 equal something, y equals 0, 0 plus C1 mu y equals 0, 0 plus C2. When you apply, substitute first boundary condition here, you get C2 equals 0. Do you understand? Oliver?
Yeah.
So you apply the same. You apply the second equation. U equal to capital U inside this equation at y equal to A. So you replace y equal to A. Y equal to A. You know that your C1 is 0. So this one you can cancel. So you arrive at what is C2. You will get this value. Do you understand?
Yes, sir.
Okay. So after you get the C1, C2, you substitute back into this equation. So C2, 0. You replace this whole thing into here. Your velocity profile equation will be this one. Okay, you arrive at U equal to capital Uy divided by A plus A squared divided by 2 mu dp over dx and the y over A ratio here with the A exponent here. Okay, so you substitute the C1 just now and then you rearrange, you'll get the velocity profile for moving plate. This plate is moving at U. Before this, the case 1, because of the differences of pressure, these two plates are not moving. Before this, the first case that we discussed in our previous lecture. These two plate doesn't move. These two plate doesn't move. But today, our lecture, we will consider upper plate is moving now with constant speed U. So we get the new equation for our moving plate. If our top plate moving, then you need to use this velocity profile equation. Understand? Do you get it, Ku or Oliver? Do you get it?
Yes, sir.
Okay.
Yes.
All right. Okay, Amir is here already. Okay, good. All right, so the next one, because of the Newtonian float, we can use the shear equation. Shear stress, shear yx equal to mu du dx. We were going to rewrite our velocity equation in terms of shear stress. All right, so we will replace this equation with a Newtonian equation. So you rewrite this equation. So the shear stress equal to mu du dy. So you have this u equation. You differentiate with y. You take this u, you du dy, you will get this equation. Right? So this equation is from du dy times the mu. You take the first equation, you differentiate it, you'll get this one. Then you get what is the definition for shear stress in the Newtonian float in terms of velocity profile. So you'll get u divided by a plus a squared divided by 2 dp over dx and the constant value over here. Okay, then you can further rewrite, rearrange your shear stress equation in terms of capital U and A and dp dx and y divided by a, so on. So you have two equations for shear stress. And these two equations, or these three equations that you see on the screen here in orange color, this one apply for moving plate, for a plate that is moving. One of the plate is moving. Then you use these three equations. Okay. All right. Then we need to find the volume flow rate also. So volume flow rate given you by Q equal to VA, velocity times area, and we can rewrite in terms of L. So you modify a little bit, your dA equal to L dy, like what we covered in previous lecture. Your area changed to L times dy. You get an A cross section of your pipe, L dy. Your V vector here is your U, and you integrate from 0 to A. From 0 to A, you do the mathematics by substituting this equation, the velocity profile for one moving plate. You will arrive, this is just, again, this is a mathematics substitution. So you substitute your U inside U, this U inside here, and then you move your L to left hand side. So you get your Q in Q divided by L and the integration of your velocity profile equation from 0 to A dy. So you have a mathematics steps for integration. Yeah. So if you do not know how to do integration, go back and polish up the integration steps or skill. In this module, you need to use the differentiation and integration skill to get the answer. And after that, you can rewrite. You can, after you integrate, you will get this answer. Q divided by L equal to UA divided by 2 minus 1 divided by 12 mu dp dx and A cubed. So this answer is from the products of your integration steps. Okay, you arrive at this equation. Then after that, we can use to define our maximum velocity. So again, I already explained about the parabolic, or not parabolic, the quadratic equation, y over x yesterday, or in our previous lecture. When you have a quadratic equation, ax squared plus bx plus c, you want to get the maximum point, you use equals 0. You get maximum point here. So this one is from your quadratic chapter in your mathematics class. So you want to get the maximum velocity, you will use the differentiate equation, du over dy. You take this velocity profile equation. Again, this velocity profile is for moving plate. If for upper plate is moving, then we use this equation. U equal to this one, whole thing. You du dy, you take this one, du over dy. So this whole equation is dy. Okay, you differentiate this whole thing. Then you will get this equation, right? U divided by A plus A squared plus 2 mu dp over dx and the constant value. Okay, and further simplify this one. So you can look at the screen. So you know that at maximum point, du dy equals 0. At the location where your y will be A divided by 2, means that this whole thing equals 0. This whole thing equals 0. And you rearrange the equation, you'll get your y, right? Means you take this whole equation equals 0, and then you rearrange, put your y to the left hand side equal to what? So it means you rewrite this whole equation equals 0, and then you rearrange the whole equation in terms of y. So y equal to what? So when your du dy equals 0, you get y equal to A divided by 2 minus u divided by A, and so on, from the product of this simplification. Right, this is a mathematics steps. Any question to ask me? Anything that you're not clear? Ask me now, or I will ask you to explain now. Anything that you're not clear? Okay. So the notes here you can see. So for moving plate, if your two plate is moving, it's very hard to find the Umax. it's very hard to find Umax because the equation that you see here is not a very direct equation. If you have a two parallel plates that is not moving, U equals 0 here, U equals 0 here, then you can use the previous equation where you get a max U max here. Okay, U equals 0 at the wall, U equals 0 at the wall. But today we'll look at one moving plate on top. So when the plate is moving, this is stationary, U equals 0 at the bottom. If your upper plate is moving with the capital U, then the profile of your U is changing already. Your profile is become this one. The U profile become this one. And the U max is not very easy to find. You need to use calculation to calculate. All right. You can see, you can see the difference between the stationary plate and the moving plate cases. Clear? All of you? Amir, you able to understand?
Kind of, sir.
Good, Amir?
Yeah, trying to understand, sir.
All right. So trying to understand means you still not yet get it, is it?
Yeah.
All right. So which part you're not getting it?
Maybe the last part of the point of maximum velocity here.
Which one?
The equation that
This
after
one.
the
This one.
yeah.
Okay. So by looking at the drawing that I draw on the screen here, you have previously, before today, I think last class, what we mentioned is that we have a two parallel plates that is not moving. This one you understand, right?
Yes.
Amir?
Yes, sir.
Yeah. So previously, all the equation that we use cannot be used today because today we are considering a moving plate, with this one plate is moving above with the capital U speed. So when you derive the velocity profile equation, you see that you are reaching this equation, U equal to capital Uy divided by A plus A squared divided by 2 mu and so on. So this one we derive from the boundary condition just now. So we need to use the U profile inside this case. We use this equation. This equation is for this case only. You cannot use in the stationary, both plates stationary case. Do you understand this one, Amir?
Yeah.
Yeah. Okay. Then you want to find the maximum velocity in this scenario, in the moving plate scenario. You will still use the differentiation method where you will differentiate this whole equation. You differentiate du over dy. So you differentiate the whole equation with y, you will get this equation. So Amir, you understand this equation, how you get this one?
Yeah, this one okay.
Yeah. So when you put the whole thing du dy equals 0, then you rearrange, you'll get your y, correct, Amir?
Yes.
So your y equal to this one, your y equal to this one. So it's not very direct. Is you take your a divided by 2 minus something. So it is not at the middle, because previously your a is at the middle, right? I mean your center line is a divided by 2, correct?
Yeah.
But today, if your u is moving, there's a negative component there, so it will move down a little bit. It will no longer in the center. It will maybe move in this case in negative lah. So we know that it is something that is below the center line. Does it make sense to you if I explain like this?
Yeah, it's okay.
Yeah. So is it all right for Oliver and Ku?
Yeah,
Do you
sir.
understand now?
Yes.
Yeah. So don't confuse by the mathematics equation that you have. try to understand the concept. Right? Right. So that's why the blue line that I mentioned here is not very direct. There's no direct equation to find the maximum velocity for a moving plate. Before this, if these two are parallel and not moving, then you can use the previous one, which is the one that we see in all this equation. All right, both plates are stationary that we derive. Okay, then you can use all this. This equation that you see is for both plates are stationary. Then you see this one. Then you will see that when we find the maximum velocity, you will see that it's actually at a center here. The average velocity will be at the center, the Umax. If you find the Umax, so you will find that if this one equals 0, you rearrange the whole thing in terms of y, you will get y equal to a divided by 2 at here, maximum. So Umax value is very direct from the equation if the both plate is not moving. So today, when you look at one of the moving plate, right? One surface is moving plate, then it's a different equation already. Okay, then is you need to use this equation. Okay, all right. So this is the equation for today. When one of the moving plate is moving, then you use this equation for velocity profile, and you want to find the maximum velocity, you use this equation. All right, and the volume flow rate also you use this equation for moving plate. Okay. Amir, you clear now? What is happening now? You clear with all this equation, right? All right.
Yes.
Then the next one, we look at one of the diagram here. So this is a diagram where previously I explained about y divided by a is a dimensionless dimension. So if you plot y divided by a by using this equation, so you'll get all this kind of shape. So you will see that if you plot the equation, you use Excel to plot from 0 to a. You use Excel to plot 0 to a. You will able to plot the shape of the velocity. Velocity here. So by using this equation, you see that the shape from the Excel is not same with the previous section. All right. So if your u is moving, you see that the velocity is maximum velocity is moving a little bit, and you do not get a perfect parabolic shape. Okay. Right. Let's look at one example on how we apply this equation. So on your screen now, you're seeing there's a 2 circle there. So one is in the middle with diameter 76 mm. The length is 31.75 mm. The distance between the inner and outer circle is 0.6 mm divided by 2. Okay, mm. So what do we have here? We have a crankshaft journals bearing in the automotive engine, and then is lubricant with a lubricant oil. The grade of the name of the lubricant is SAE 30 oil. The temperature at the engine is 100 degrees C. The bearing diameter is 76 mm. Diameter clearance is 0.6 mm. So diameter clearance means the both side of this one is 0.6. So that's why when you calculate the A, you have to divide it by 2. Yeah. And the shaft rotate at a certain speed, 360 RPM, 3600 RPM round per minute. So the length of your crankshaft will be 31.75 mm. Bearing is under no load. So bearing is no load, so that the clearance is symmetric. So symmetric cases. Determine the torque required to turn the journals and the power dissipated. So we need to find the torque and power from the velocity profile that we just learned just now. All right, how do you solve this one? So the first one, you know that the A, you should divide it by half. So you take 0.06 divided by 2. And then the lubricants, the fluid that we're using here is SAE 30 oil, 100 degrees C. So if you see this kind of name, you should already know how to refer to Appendix A, right? We already showed you in detail in last lecture. Okay, so you should know where to find this one. SAE 30, 100 degrees C, and remember there's a difference between different graph. One graph is for kinematic viscosity, one is for dynamic. We are using the dynamic viscosity. So the speed is 3600 RPM. So you need to change this RPM into a certain parameter. So Appendix A, so don't confuse between the A2 and A3 like what mentioned in the previous lecture. We are using A2 with the dynamic viscosity with the mu symbol here, Newton second over meter square. So our property, our fluid property here is SAE 30 oil. So you are referring to this line. Yeah? You're referring to this line. So make sure you already download the Appendix A at this moment. Right. So how to use this one? Quite direct. So you're having 100 degrees C. You just draw from the graph, from the table, from this chart A2. You draw a straight line at 100 degrees C, and then you read from right to the left there. Okay, you follow this line, the intersection line of SAE 30 oil. You read to the left. The value will be about 9.6 10 power negative 3 Newton second over meter square. Any question? Any one of you do not know how to get 9.6 10 power negative 3?
No, sir.
Clear? Cool, Oliver?
Yeah.
Clear? All right, very good. So, in an exam, it depends on the resolution of your graph. I will accept if your answer is you're not able to write 9.6. If you write 9, I will accept the answer. If you write 8, then it's wrong because 8 is over here. It's not touching 8. So if your answer is 8, then you get the wrong answer. If you write 10, also wrong. Huh? It is between 8 and 10, so it's about 9. Okay, about 9.5 there. About 9 is correct. Okay, so just take note on that. All right, we need to find torque and power. So because the gap is very small, we can simulate the situation that we have here. The crankshaft movement is equivalent to a moving plate. So there's a plate is moving. On the top, there's a stationary plate. At the bottom, the distance is A. Right? So the A in this case is 0.06 divided by 2. Divided by 2. So you have to be familiar with these terms in the question. So if you're given a diametrical clearance, it means that the differences between these two circles, this side plus this side, will be 0.06 mm. So don't straight away use 0.06. You are considering the gap between the two walls here. So this two wall is actually 0.03. Okay. We're back to our question. So we can simulate with one individual moving plate at the top. Is it clear for all of you? Does it make sense that we are using a scenario of a moving plate? Yeah?
Yes, sir.
Okay,
Yeah,
good.
so
Right. So we continue with our calculation. We're going to use the governing equation. Shear stress equal to this one. Yeah. So again, you can refer back to the previous slides. Yeah. So don't worry about the the format or the detail of the content of the equation. All this you can refer back to the PowerPoint slides later on. Important that is that you understand the procedure or the principle behind on solving question. So we are using the shear stress equation, and this one shear stress is for the moving plate. So if both plates are not moving, then this equation doesn't apply. You have to refer back to the correct situation or correct case. In this case, one plate is moving, so we're using this shear stress equation, and we have all these assumptions, right? Laminar flow, steady flow, incompressible, fully developed, and there's a finite width there. So in this case, we can assume, because the flow is symmetry, so dp over dx we can put as 0. In the statement also, it tells you that the bearing have no load, meaning if there's no load, meaning there's no differential of pressure between these two. dp over dx means the pressure difference with the distance of x. So if there's no loading and the flow is symmetry, means there's no pressure difference. So this term becomes 0. I understand why we can cancel this one? Is because there's the statement, the question already tells us already there's no load at the bearing and the flow is symmetry. So the pressure difference is same. So this one you can take out, becomes 0. So 0, so the whole term, the second term, the whole thing equals 0. We only consider the first term. So we can write our shear stress equal to mu u dA. And this mu is from the chart that we just read just now, from your appendix A, chart A2, the mu, dynamic viscosity. All right. Then you need to recall back your mechanics chapter or module, how to find your velocity at the rotating body W. So your u equal to omega times the r. R is the radius from the center. Right? U equal to omega r. Omega is your rotation speed. Okay, so just recall all these are, we assume you already know already. So u equal to omega r. Then you convert, because we are using diameter in this case. So of course in exam you can straight away substitute all this number, but we are deriving equation. So we write r in terms of d, so you can write this equation become mu w or omega d divided by 2, because r equal to d divided by 2. And from the fluid appendix A data just now, we know that mu equal to 9.6 or 9, 9 times 10 power negative 3. Then you just substitute all the value there. Remember to change the round per minute into radian per second. Yeah, take note in exam, if you're giving RPM, you need to change your RPM into radian per second. You need to know how to change. So one cycle is 2 pi radian. So we're given round per minute. So you need to change 1 round equal to 2 pi radian equal to 1 round, means that 360 degree. 1 round equal to 2 pi radian. You need to divide by 60 seconds, right? So you do the conversion. Then you get the answer for your shear stress. All right. So I'm not giving you the answer. You need to use your calculator to calculate all this value. You get shear stress. Important that you understand how to get the answer. All right. Because in exam, all these things will the fluid will be changing, the value will be changing. So important is know how to get the u, how to get the mu, and all this. So from all this calculation, you get your shear stress. Shear Yx equal to certain Newton over meter. Then after that, you use this equation, torque equal to force times R. So this one you learn from your physics class. What is the moment or torque? So if you have a force that is perpendicular to a certain point, so this one is, you get the torque or moment equal force times d, or distance from here. But we are looking at the radius, so your d is radius, t equal to fr. So you just substitute the equation. So how to get f? Why this one come out like this? What is shear stress? Shear equal to force divided by area. So force equal to shear stress times A, area. So you just substitute this equation into here. How to get area? Area is this one. The area will be, the area in this case will be, cross-section area will be 2 pi r times the L of the cylinder body. Okay. Now, okay, you substitute into here. So 2r equal to d pi d times L. You get your force, right? You get your area. So you replace the F equal to shear stress pi d L times R. And then you just proceed with the mathematics procedure. You'll get something like this. So at this stage, you already can get the answer already by substituting all the numbers. This is just to make the mathematics looks more tidy. So pi 2, you just change the R into D dimension, you'll get this equation. Then you can substitute all the answer. Because you have the D, you have the L, you're able to find the torque of the system. T equal to Fr. So just recap. Today you need to recap two equations. One is T equal to Fr. And when you have an omega rotation, U equal to omega R. Right? This is just a recap from your physics class. Then after the power equal to F times U, or force times the speed or velocity. Force times speed, force times velocity, you'll get the power. Okay. Now power is the change of work. All right. What is work? Work, you push something to a certain distance, right? Work. So power equal to power, the symbol of power is W dot. The change of your work equal to force times velocity. Again, how to find velocity is R omega or omega R. Omega is the rotation speed, or rotation speed. So Fr is your torque. Omega is given. So you substitute all the value inside this equation, you get the power in watt unit. Is that clear for you guys?
Yes.
Yeah.
Right. Okay. So we have these 3 omega power already. So the next one will be a normal procedure to check whether you're having a laminar flow. Just check the Reynolds number. Again, Reynolds number equal to rho Vd, right? Rho Vd. So our velocity is capital U. A is our distance divided by mu. Again, our float here is not water, is lubricant oil. So you need to take the Sg times the rho water for the rho. You need to do conversion for the rho by using Sg times the rho of the water, density of the water. All right, so if you substitute, you'll get some value. And if the value is less than 2300, then confirm is laminar. Of course, this question will be surely as a laminar flow. All right, for your info. Okay. All right, so okay, let me stop the recording.